Oh, okay, yeah, I was watching a cat video. Okay, that's what I do in my free time. Judge me. I don't care. Okay, well, let's get to business. Let's talk about lesson 1.2, Introduction to Transformations. Now, I will say you probably remember this from middle school because you have talked about this before. Transformations, there's four kinds that we're going to discuss. All right, and a transformation is a change in location or size of any figure. Okay, that is a transformation. Just changing the size or location. And there's four ways we're going to do that. The first one, now I'm going to give you a chance. Try to name it before I do. And I'm going to go pretty quickly here. So maybe pause the video. What's this transformation called right here? This is a translation. Okay, and a translation is otherwise known as just a slide. Okay, when you slide a shape. So if I take a shape and I slide it on over, that would be considered a translation. The second one that we're going to be talking about is a reflection. Okay, and another word for a reflection is just a flip. So if I flip something over, like we see here, a flips on over to here, that is a reflection. And I just want to say, yeah, I put that prime there before. Remember, A is where you start, and A prime, that means after the transformation. Okay, number 3. Well, what's happening over here? I will give you a clue. The wheels on the bus go round and round. That's right. It's a rotation. Dope. So we got a rotation going on over here, and another way to call that is just a spin. Okay, wheels on the bus go round and round. So if you took this square and you spun it, otherwise rotated it, that's another way to change its location or size. And then finally, we have our best friend. Our best friend is called the dilation. Okay, and a dilation, as you can see here, is when a shape or figure or any of these geometry terms gets bigger or smaller. So we call this growth or shrink. Okay, growing or shrinking, any way you want to put it. Okay, and that's a dilation, gets bigger or smaller. Now that's the four kinds that we're going to be talking about through the rest of this unit because it's really all about transformations. But there's this main word you really got to know. This is some vocabulary, a rigid motion. Okay, it is really important that you know the definition. And a rigid motion is a transformation where the lengths of the sides and the angles of the figure stay the same. So after the transformation, everything stays the same. Okay? So the side lengths don't change and the angle measures don't change. And I'll give you a clue. If you look at these four different kinds of transformations here, okay, 3 of them are rigid motions, meaning the sides don't change and the angles don't change. And one of them is not a rigid motion. So let's go through it and figure out which ones are rigid motions and which ones are not. So for our first one, if I slide a shape like so, did I change the angles or the side lengths? Well, the angles look the same and the side lengths stay the same, so this is probably, and it is, a rigid motion. If you slid anything really, right, it doesn't change the size or angle measure. Now over here, if you reflect something, does that change the sides lengths or the angles? No, nothing changed there, right? Just the location. So that is also a rigid motion. Our third guy, a rotation. When I rotate a figure, does that change the length of the sides or the angle measures? Well, let's look. Just use your eyes. Does any of those things change? Nope, no change. So these are rigid motions. And then we come to, once again, our best friend, the dilation. And does this change the side lengths or angle measures? And the answer here is yes. Obviously, the sides are getting bigger. If this was 5, we could say that this is 10, right? It grew in this case. So this is not a rigid motion. Okay? But our other 3 guys are. Now I will say in a dilation, the angles do stay the same. Alright, all your angles do stay the same. It's only the side lengths that changed. And that piece of information will come in handy a little bit later in the course. So, if you're looking over here, if I said, is this an example of a rigid motion? What would your answer be? Here's our pre-image. Remember, that's before the transformation. And this is our image. You see those little marks right there, so we know it's the image, A prime, B prime, C prime. Would this be a rigid motion? And I would say that that is yes. Why? Because this is a reflection, Okay? So this is a reflection. So yes, a reflection is a rigid motion because the the length of the sides and the angle measures stays the same. So I'll show you why it's important that we learn about rigid motions, and it's going to help us prove some things. Now, the next part of geometry is how do we prove that two shapes are congruent, okay? How do we know they're exactly the same size and shape? All right? Well, one way we're going to do that, and there will be more, is that if we could show that two shapes will map right on top of each other, then we know all the sides and angles are the same. Let me say that again, okay? Let's go back. What is congruence? Okay? Congruence, or shapes are congruent, if all the angles and all the sides are the same. That's how you know two shapes are the same. All the angles and all the sides are the same. We know that two shapes are congruent if we can map them onto each other. So let me show you this example. How do we prove that ABCD is congruent to XYZW? Well, if I can show that I have a rigid motion that will map these onto each other, I'll know they're congruent. Watch and let's see if we can do this. I'm going to use a translation. I'm translating this rectangle over and boom. You see how they map directly on top of each other? For that to happen, that means all the sides and angles had to be the same. Okay? The side lengths had to be the same and the angles for them to map onto each other. So since they do map right on top of each other, I know that a rectangle ABCD is congruent to rectangle XYWZ. Okay? And I used a rigid transformation, so I didn't change the angles or the sides, so they must be the same. Now, is there any way using a rigid motion to map ABCD onto LEMG? Well, let's try it out. We can try translating it. That doesn't work. They don't map perfectly on top of each other. We could try rotating it. Nothing's happening there. We could even try reflecting it. See, flipping it. Let's try flipping this guy. Didn't do anything, right? So no matter how many rigid transformations I use here, there's no way to get the map onto each other. So I actually know that these are not congruent figures. So I cannot prove that these are congruent. So rectangle ABCD is not, I'm not sure if you remember that symbol, not congruent to rectangle LEGM. So once again, I want to tell you this point. We could prove two figures are congruent if there's a set of rigid transformations that map them onto each other. Because for them to map onto each other, they must have the same side lengths and angle measures. So let me show you how to do a quick proof here, right? Using some rigid motions. First, what we're going to do is figure out, can we map these two triangles onto each other? Can I map x, y, z onto x prime, y prime, z prime? And the answer here is yes. I can use a rotation to map them onto each other. So this is a rotation. All right, so we can use a rotation. If you don't believe me, let's actually rotate it. So I'm going to take this triangle. All right, let's take our little triangle, and I'm going to rotate it around. All right, and let's see if they map right on top of each other. They sure do. So all I had to do was rotate it and translate it, but we're just going to say we had to rotate it here. So we do a rotation, okay? Now, since I can map them onto each other, I know they must be congruent. So let's explain why triangle XYZ is congruent to triangle x prime, y prime, z prime. So let's do that. So a rotation, you can just fill in these words, maps triangle XYZ onto triangle x prime, y prime, z prime. The next part of the statement is a rotation, and so since a rotation maps them onto each other, a rotation is a rigid motion, and rigid motions preserves the side lengths and angle measures. So all I had to do was state, well, I used a rotation to map them onto each other, and since I know a rotation doesn't change the side lengths or angle measures, they must be congruent, right? Because they didn't change the angles or the sides. Let's try that one more time. So in this second case, do we know that CAT and DOG are congruent? Well, first let's figure out if we can figure out a transformation that would map them onto each other. And in this case, I can use try to beat me to it, reflection. Okay, we can use a reflection. Don't believe me? Let's check it out. I'm going to just reflect this guy over. Whoop, whoop, whoop. Up, down, reflect that, and look, they map perfectly onto each other. So a reflection gets us mapped onto each other. So now we're going to use the properties of rigid transformations to explain why triangle CAT is congruent to triangle DOG. And by the way, if you saw that I used rigid transformations, that is the same as rigid motions. Okay, you can use either word. So let's explain why they're the same. So a reflection maps triangle cat onto triangle dog, and a reflection is a rigid motion and preserves the side lengths and angle measures. Okay, so that is enough to prove that they're congruent. I used a rigid motion to map them onto each other. That must mean that the side lengths and angles must be the same. Okay, so if you're ever wondering how do I write out my proof, you can use this sentence right here. Just fill in those words and you'll be good to go. So that's it for this lesson. Let me give you a tip. Go home, kiss your mama, say I love you, and then go drink some milk. Goodbye.